So today we're going to talk about the fundamental theorem of calculus, which is obviously a pretty important theorem and the basis of everything we're going to be doing with integrals from here on out. So kind of a big deal. Um, Before we get into the actual theorem, I want to kind of do a really big overview recap of what we've been talking about. The first month or two of school, we were looking at differential calculus. And we're not done with derivatives, but everything was about derivatives, right? So we started out the year saying, let's find the slope of a secant line, the line between 2 points. That slope would be delta y over delta x. And derivatives are when we allow that delta x to approach 0 so that the 2 points are essentially the same point, and therefore we can find the slope of a tangent line at one points of tangency to the curve. So so we used limits to find tangent slopes. And so when we're taking derivatives or using differentiation, we always get a quotient, a delta y divided by a delta x. When we switched over to integrals in chapter 4, now we started looking at areas. And integrals, remember, represent the area between the curve and the x-axis. And we can start by just using rectangles. The area of a rectangle would be delta y divided by delta x, or I'm sorry, delta y multiplied by delta x. And what we were interested in was shrinking these rectangles down and using them to approximate the area underneath a curve. And when we approximated with Riemann sums, lower sums underestimated the area, upper sums overestimated, and midpoint and trapezoid were somewhere sort of in between. As we allow the number of rectangles, or the size, the width of the rectangle, delta x, to approach 0, so the number of rectangles approach infinity, then we get the actual area underneath the curve. And again, it's still some sort of product. So when you're integrating, you're finding area, and areas are products. When you're differentiating, you're finding slopes, and slopes are quotients. And remember, they're inverse relationships. So when you take the derivative of an integral, they cancel each other out. You're left with whatever the function is. When you take the integral of a derivative, same thing. Those are inverse operations. And we used limits to sort of prove how we can get exact values for areas under curves and exact values for derivatives and slopes. So what is the fundamental theorem of calculus? You're allowed to abbreviate it as FTC. If a function f is continuous on the closed interval a to b, then the integral from a to b of f prime of x dx will be equal to f of b minus f of a. When you take the integral of the derivative of f of x, you're going to get f of x plus c. And then when you put these limits and make it a definite integral instead of an indefinite integral, you're going to get a numerical value, an actual area for that portion of the graph between the curve and the x-axis. The area is a net area between f of x and x-axis on a to b. We talked about that in the last set of notes, where these are really just net areas. We didn't talk about this shortcut. We've been using the limit process to come up with that value, but yeah, it's kind of cool. It works out to be f of b minus f of a. And you can rearrange the terms here, because the integral from a to b of f prime of x represents a change in position, essentially. Like, think of it this way. The integral of a velocity function would give us the position function. So we could think of this change in position. So if I wanted to find like an ending position, for example, if I wanted to find f of b, where does the particle end up at the end of 5 seconds or whatever? That would be equal to f of a plus the change in position, the integral from a to b of f prime of x dx. All I've done with this equation is manipulate the first equation in FTC. I've just added f of a to the left side and, flipped my equation around. So f of b is equal to just this rearranged equation. And again, this is saying f of b equals f of a plus the net change from a to b. Now, there are a lot of different ways to prove this, and if you hop on YouTube, you'll see proofs where they're also sketching parts under the curve, so they're kind of using some geometry to help you understand this. I'm going to vary slightly from what my answer key says, because I think the proof, the really formal proof from our textbook, can get kind of confusing. So I'm going to call this a semi-proof. I don't want to just say, like, here's the rule, let's use it. I want to at least kind of show you why it works using what we've been doing. So if we were going to use the limit of Riemann sums to evaluate a definite integral, which we've done before, we would start by saying the limit as n approaches infinity of the sum from I equals 1 to n of delta x times, instead of f, normally I write f of xi right here, but I'm going to write f prime of xi right here because this is an f prime function in here. And then normally we say, all right, delta x is equal to the endpoints, b minus a divided by n, and there's no simplifying that really. This is where my proof differs from if you pull up the PDF on the Schoology Notes folder. I have it written as xi minus 1, and I just think that's a bit more complicated than what we really need to kind of understand the mechanics here. So anyway, normally we write down something that we could sub in for f of x sub I, but we can't do that right here for now because there's no equation. I can't say like, oh, it's x squared, and I'm going to sub in x squared. So I'm just going to keep that as it is. So now I have the limit as x approaches infinity of the sum from I equals 1 to n of b minus a over n times, actually, let's not write f prime sub x sub I right now. We have to have something to sub into that. So what are we going to put in? I need some sort of an expression. Remember, x sub I represents an endpoint of a rectangle, and it can be anywhere. It doesn't have to be at B, it doesn't have to be at A, it can be anywhere on the interval. And somewhere on the interval, the mean value theorem says that there should be an f prime of c is what we normally use, but an f prime of x sub I such that that derivative slope is equal to the secant slope on the interval, f of b minus f of a over b minus a. Right? So maybe I let the xi that I'm talking about for this problem be whatever that value is. So I don't know where it is, but is it the third subinterval? Is it the fourth? I don't know, whatever. It's anything. But I'm going to use that. So I'm going to say, well, let's swap out f prime of x sub I with the mean value theorem that says one of those x sub i's, it's going to equal f of b minus f of a over b minus a. And that's kind of handy, right? Because you can see like, oh, this b minus a cancels with this one. So now I have the limit as n approaches infinity of the sum from 1 to n of f of b minus f of a divided by n. I don't have any i's that I have to worry about with those I formulas. So when I take the sum of this, I have to think about, what is this? F of b is a function value, right? So that's a number. F of a is a number divided by n, which will be a number. So this is a constant right here. So my rule for summing up n terms of a constant is to write this as the limit as n approaches infinity of the constant, which is f of b minus f of a over n, times n, right? If the constant is 5 and you're adding it up n times, it's going to be 5 times n. Well, the constant is f of b minus f of a over n, which I'll multiply by n. Those n's cancel. I have the limit as n approaches infinity of some numerical value, whatever f of b minus f of a is. And the limit as n approaches infinity of that is just that constant value. So it is f of b minus f of a. So pretty cool. So we just went through and showed kind of a semi-proof. It could be more formal. But when I used what I know about limits of Riemann sums, I got that the integral from a to b of f prime of x dx did work out to be f of b minus f of a. And again, it's not f prime of b minus f prime of a. It's whatever f of x is, whatever that equation is, subtracting the endpoints of those function values. So as long as you can find the antiderivative of f, now you have a way to evaluate a definite integral without having to use that big limit process. So that's exciting. Some notation that we want to be familiar with, the integral from a to b of just f of x dx, so not f prime, but just any f of x dx, it's equal to the antiderivative, capital F of x, so whatever equation you get for that, evaluated from b to a. And then that's equal to whatever you got for the antiderivative, plug in b, and subtract the antiderivative evaluated at a. Another way to write this, so I used square brackets here. You'll also see the antiderivative, and then they just use a line from b to a. We kind of did that with evaluating derivatives too. Like, okay, now find dy dx evaluated at the points 1, 2. So we use that line and put the ordered pair down here. It's kind of the same thing. So I don't care how you write it. Sometimes I switch back and forth. Sometimes this way looks a little more streamlined to me, so I use it. It just kind of depends. And why don't we have a plus c, by the way? What happened to our plus c? Because for definite integrals, it was always like, there could always be a plus c somewhere. So if you think about this, if you take the integral from a to b of f of x dx, the indefinite integral, the antiderivative, would be capital F of x plus c, right? Evaluated from b to a. And so when you plug b into that, you're going to get f of b plus c. When you plug a into that, you're going to get minus all of f of c, sorry, not f of x, f of a plus c. And when you distribute that negative through, c minus c cancels out, and you're left with f of b minus f of a. Again, those capital F's represent antiderivatives. So, if the original equation was x dx, and we take the integral, we get x squared over 2, and then we plug in b to x squared over 2, and plug in a to x squared over 2. And that's what we're going to practice in the next part. So let's evaluate some definite integrals. This is supposed to say dx right there. So the integral from 1 to 2 of x squared minus 3 dx. We don't have to use our limit notation. All right, so let's take the integral of each term. I'm trying to decide, I don't know why this is such a big decision. Do I want to use square brackets or not? I'm going to use square brackets on the first one. The integral of x squared, or the antiderivative, is x cubed over 3 minus 3x. Evaluate from 1 to 2. And then remember, the order in which you subtract makes a difference. So it's got to be 2 first and then minus 1. So plug in 2, you get 8 thirds minus 6 minus 1/3 minus 3. I suggest using parentheses just so that we're being careful here. 8 thirds minus 18 thirds is negative 10 thirds. And then minus 1/3 minus 9 thirds is negative 8 thirds. So plus 8 thirds. And so we get negative 2 thirds for our area. This still represents the net area under the curve of x squared minus 3 from 1 to 2. You could sketch that graph and kind of verify whether or not it should be negative. All right. Now I'm going to use not the square brackets, but that vertical line so you can see the difference in notation. What's the antiderivative of secant squared? So that should be tangent x, right? Because the derivative of tangent secant squared. And then we're evaluating that from pi over 4 to 0. Or I always say that backwards. It's from 0 to pi over 4. But in my head, that's what I'm thinking. So this is the tangent of pi over 4 minus the tangent of 0. The tangent of pi over 4 is 1. The tangent of 0 is 0. So my net area is 1. Next one, remember this is 3x to the 1/2. So we would get 3. When you add 1/2 plus 1, you get 3 over 2. So it's going to be 3 times 2/3 x to the 3 over 2. And then we're evaluating that from 4 to 1. The 3's cancel out. So you have 2 times, now I wouldn't leave this as an exponent. I would change it to its root form. 4 to the 3 over 2 is square root of 4, and then you cube it. And there's no plus or minus because we didn't generate, like we didn't square root both sides. It's already in there. Minus 2 times, I guess it doesn't matter here. 1 to the 3/2 doesn't matter. So 2 to the 3rd is 8. 2 times 8 is 16 minus 2. So that net area is 14. All right. Number 2, find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines 0 and 2. So what's our area equal to? Well, we're taking the integral from 0 to 2 of 2x squared minus 3x plus 2. Don't forget to write dx with respect to x here. And let's find the antiderivative of each term. So x squared becomes x cubed over 3. So you have 2x cubed over 3 minus 3x squared over 2 plus 2x evaluated from 0 to 2. Right? When you put 2 in, you get 16 thirds minus 3 times 4 divided by 2, 3 times 2. So minus 6 plus 4 minus, when you plug in 0, you do get 0. It's worth checking that, like just a quick check to make sure, because if there were some constant term, I'd have to remember that's like, oh, it's not minus 0, it's minus 2 or whatever. So this is 16 thirds minus 18 thirds plus 12 thirds. So negative 2 thirds plus 12 thirds is positive 10 thirds. And we can see in the graph, we should have had a positive answer because this whole graph is above the x-axis. What about an absolute value graph? So you have to think about this. Now, you could think about the graph itself. It's absolute value, right? So I think it might be in our best interest to kind of graph this thing, right? Like its vertex would be at positive 1/2, and it's got a slope of 2. If you plug in 0, you're going to get 1. And let's see. So that's our starting point. And then when we plug in, so I know it goes down like this. And then when we plug in 2, because that's our end point, when you plug in 2, you get 3. Okay, so I could just do this geometrically, right? What is this area? So geometrically, it would be, well, that's 1/2 times, the first one has a base of 1/2 and a height of 1, plus, both are positive areas, 1/2 times, this base is 1.5, 3 over 2, and its height is 3. 1/4 plus 9/4 is 10/4, or 5/2. Done. What if I wanted to do it a more complicated way? Well, I would have to think about like splitting this into, I guess, a piecewise function, right? Take a look at the graph. You'd have to say, well, from 0 to 1/2, we've got the line negative 2x plus 1. So you'd have to think like, okay, absolute value of 2x minus 1 equals negative 2x plus 1 if you're on this interval, 0 to 1/2. And then for anything bigger than 1/2, between 1/2 and 2, you've got the line positive 2x minus 1, right? Because that's a positive 2 slope, and the original intercept was minus 1. And that's for anything between 1/2 and 2. It doesn't matter where I include the 1/2 on this. And then you would have to integrate separately. You'd have to say this integral is equal to the integral from 0 to 1/2 of negative 2x plus 1 dx plus the integral from 1/2 to 2 of 2x minus 1 dx. And let's see if we get the same thing. So this one will become, since this is x squared over 2, I'd get negative x squared plus x. And you're evaluating that from 0 to 1/2. And then you're adding to that positive x squared, 2x squared over 2, minus x from 1/2 to 2. Oh, this is so much more complicated. Okay, so then when we plug in 1/2 and we square it, we get negative 1/4 plus 1/2 minus 0 plus 4 minus 2 minus 1/4 minus 1/2. Good gracious. So 1/4 plus 2, and this is going to be negative 1/4, but plus 1/4. And we finally get to 2.5, which is 5/2. Always stop and do a quick thought of like, can I just graph this? Is it really that hard to just graph this and find the area? That's why we spent that time doing that yesterday. You can puzzle through it here, but if you see an absolute value or just a little linear piece as your function, why not just graph it and find the area that way? Okay, we need our calculator for this one. A particle moves along the x-axis so that at any time greater than 0, its acceleration is given by a of t equals natural log of 1 plus 2 to the t. If the velocity of the particle is 2 at time 1, then the velocity of the particle at time t equals 2 is what? So this is that fundamental theorem, I guess with a twist, but remember, we're thinking of this as like, wait, what is our starting position? So at the beginning of the notes, we had the fundamental theorem of calculus, and then we also said, well, I could find f of b by just starting at f of a and adding the integral, the change in position, from a to b of f of x dx. Sorry, f prime x dx. Makes a difference. Okay, so what do I know here? I want to find not f of 2, I want to find v of 2. And I am given v of 1, right? I'm given v of 1. And I can say start at v of 1 and add the integral from 1 to 2 of a of t dt, since everything's with respect to t instead of with respect to x. And I can sub in what I know. V of 1 is equal to 2 plus the integral from 1 to 2. We're going to use our calculator. So this equation is natural log of 1 plus 2 to the t dt. And that will be v of 2. We'll see what the calculator tells us. So hop over to your calculator. So I'm going to type in this exactly, 2 plus. The integral feature is found in Math 9. And if you have math type, it's really nice because you can see what you're supposed to be plugging in. I'm going to be honest, if you have an 83, I do not know the order. I'm assuming the order in which you type things with commas is the same as how I'm typing it in, but that's something we will need to Google or look up. The function is natural log of 1 plus 2 to the x. We can't put t's in here. I needed to close parentheses around the natural log because this parentheses is just, the big one that we have right here. And then that needs to be an x as well. So this is already 2 plus that value. So this is 3.346. Let's see if that's one of our choices. Yeah. All right. So you're still using FTC. It's just that you've rearranged it to solve for either f of b, or you could also do the same thing to find f of a. What is the exact total area bounded by the curve f of x equals x cubed minus 4x squared plus 3x and the x-axis? So if we're talking about total area, then we need to think about where is it positive and negative. Now, if this were a graph, I want to show you on the calculator first. If we were allowed to use a graphing calculator for this, anytime I see total area, just like I saw total distance, I don't want net area. Net area is adding and subtracting areas to see what you have left over. Total area is forcing negative areas to be positive and just saying, oh, I have absolute values of all of my areas and just adding them together. Okay, so if we were doing this, in the graphing calculator, we would find the zeros. So we're just going to make this one a graphing calculator one. We'll do the next one without. So first we would find the zeros. We could do that algebraically, or remember, you can type it in to your graphing calculator. Type in the equation. I always zoom 6 to get it back to a 10 by 10 window. And then I can see the zeros. There are 1, 2, 3 zeros. And we're interested in the area between the curve and the x-axis. There are 2 of those. The net area will be negative. But the total area that I want to add up this plus this. All right, so the zeros are 0, 1, and 3. If I wasn't sure of that, I could use the 0 feature in this menu, but I'm not going to take the time to do that. So I want the zeros were 0, 1, and 3, right? So I want the, you can do this 2 ways. You can do the integral from 0 to 1 of, you know what, I've already typed in f of x into my y equals. If I don't feel like typing it in again, you can type, if I can get it over there, you can type in, come on, there. You can type in y1, vars, y vars, function, y1. And whatever you have entered into y1, it'll put that in there. This is the first area, that little positive area right there was 0.417. And then I want that negative area too, so I could do another, enter that and just change the parameters to be from 1 to 3. That's negative, right? So I could say, well, I don't want the negative. I want this answer minus this answer. Okay, let's see if we can take the integral from 0 to 3 and just throw an absolute value sign around everything and see what happens with that. So let's go from 0 all the way out to 3. Let's make it absolute value of y1. Gosh, if I can If I can properly type things in, math, number, absolute value, y1 with respect to x. We get the same answer. That's kind of nice. Because the absolute value of y1, it's forcing all those values that were negative to be positive. So it's graphing it as if it's like that and finding the two areas. All right, so you have options. If this were a calculator problem, what would you have to show for the AP test? You would just say that you're doing, so let's say on calc, you would have had to find the zeros or at least graph it to see where that starting and stopping point is. You could say from 0 to 3, the absolute value of x cubed minus 4x squared plus 3x dx is approximately equal to 3.083. Now, if it's not a calculator problem, we're going to do the next one non-calculator, then we need to graph, excuse me, I thought I was going to sneeze. We need to graph the equation and force negative areas to be positive just using subtraction signs. So what am I talking about? Okay. I need to think about x to the fourth minus 2x squared plus 1. First, let's go ahead and find the zeros. X squared minus 1, x squared minus 1. Each of those will be x plus 1, x minus 1, so x plus 1 squared, x minus 1 squared. The zeros are plus or minus 1, and the graph has to touch and turn at both of those. So if I'm graphing this thing, at -1, there's a 0. At +1, there's a 0. What's the y-intercept? When you plug in 0, you get 1. And the end behavior has to be up on both sides. So it looks like this. So what is the area bounded by the graph and the y and the x-axis? So that one, I don't have to worry about subtracting negatives or forcing anything to be positive. I can just say it is the integral from -1 to 1 of x to the fourth minus 2x squared plus 1 dx. So that will be x to the fifth over 5 minus 2x to the third over 3 plus x evaluated from -1 to 1. And that is going to be plugging the 1 in first. 1/5 minus 2/3 plus 1 minus -1/5 plus 2/3 minus 1. Okay. So I think I want to combine terms first. When I distribute this negative through, I'm going to get positive 2/5. Negative 2/3 minus 2/3 is minus 4/3. 1 plus 1 is plus 2. And then it's 6/15 minus 20/15 plus 30/15. So 16/15, yes, is my net area. Now, I want to go back to this one. I thought that on 6 I was going to have to split things up. What if this was a non-calculator problem? So let's go back to our little graph here. We would have graphed it. I'm going to make this bigger. We would have factored out an x and then factored. And then found the zeros. And on the graph, at each of those zeros, we know the graph crosses through. This was an x cubed graph that has right-sided behavior increasing, left-sided decreasing, crosses through like this. I don't need to know how high or how low it reaches. But without a calc, the first area is positive. It goes from 0 to 1. This is kind of what I did separately on the calc without using that absolute value symbol. So the area under the curve is here. And then instead of adding the second area, because adding the second area is going to be adding a negative number, we need to subtract the second area because we know that second area is negative. So you're doing minus a negative. You wouldn't put your own absolute value symbol around because with absolute value equations, you have to think about like the two scenarios and things just get really complicated. So you would just subtract here because you know this is a negative area. And you would get the same answer, but in its fraction form. Okay, find the area bounded by the curve y equals 2x minus 2 sine x, y equals 0, x equals 0, and x equals 3 pi. So let's do this one without a calculator. I'm not going to graph because, let's see, why don't I want to graph? Because 2x minus 2 sine x, we're on the interval 0 to 3 pi. Anytime sine is negative, you've got negative 2 times a negative value. So that's going to be a positive term. 2x is positive no matter what, because we're plugging in positive values from 0 to 3 pi. And since sine is restricted to be between 1 and negative 1, when I start plugging in angles that are bigger than 1 or negative 1, 2x is going to be a larger value than negative 2 times whatever sine comes out to. So this is positive everywhere. I guess I could graph it if I wanted to, but honestly, this is not something you would graph by hand. It is good to kind of puzzle through it like that, though. Okay, so, oh, duh, why did I have to go through all that? I didn't, because we're bounding it by y equals 0 as well. So we're saying don't worry about the part that goes below the x-axis. Gosh, got it. Okay, so from 0 to 3 pi, 2x minus 2 sine x dx. 2x squared over 2 just becomes x squared. And then, so the integral of negative sine is cosine, right? So we're going to get plus 2 cosine x. And we're evaluating that from 0 to 3 pi. 3 pi squared is 9 pi squared. And then the cosine of 3 pi, remember 3 pi is at the location of pi. So that's going to be minus 2, because 2 times negative 1. Minus 0 squared is 0, plus 2 times the cosine of 0 is 1, so plus 2. 9 pi squared minus 2 is 9 pi squared minus 4. All right, we might be running out of time. I don't know how long this video is getting, but if it's getting too long, then part of our homework is just going to be to finish this. Let g of t be the rate of growth of a population at time t. So g of t, even though it doesn't say prime on it, it is a derivative because it's a rate of change. Derivative. So interpret the meaning of the integral from b to a of g of t dt. So when you take the integral of a derivative, you get the original function. And the original function is a population function. So it's the net change in population I was going to say during times, but let's say between times A to B. Why did I say net change? Well, it is population, so we can't really have a negative population. So I could say just the change in population, but I don't want to say like the total population because I think we talked about this in class, but the total population might have had a different starting point at time A rather than 0. So you could just say the change or if I know it's an increase, or the growth. But I don't even know that it's growth because I don't know anything about the population function. So I'm just going to say change. Suppose an epidemic is spreading through a city at a rate of f of t. Huh, new people per week. That hits home, doesn't it? Interpret the meaning of the integral from 0 to 4 of f of t dt. So again, a rate of f of t. Even though it doesn't say prime on it, this is a derivative. So the integral of a derivative will come out to just the original function, which is talking about people. So not with that per time period. So this is the change. I'm just always going to be say change to be safe here, unless I know it's an increase or a decrease or whatever. The change in the number of new infections, because it says new people, so infections or new people infected, whatever, between weeks 0 and 4. Or you could say in the first 4 weeks, whatever. Suppose a rumor is spreading at a rate of f of t equals 100 e to the negative 0.2 t, new people per day. Find the number of people who hear the rumor during the 5th and 6th days. So this is always a little bit tricky because you would think it's like, oh, just the integral from 5 to 6, right? But think about this. During the first day, we've got the integral from 0 to 1. During the second day, it'd be the integral from 1 to 2. Third day, 2 to 3, etc., etc. So during the 5th and 6th days, the 5th day is going to be the integral from 4 to 5, and the 6th day is going to be the integral from 5 to 6. It's not just the integral from 5 to 6. So you just have to be careful there. The total integral should be from 4 all the way to 6. So the integral from 4 to 6 of 100 e to the negative 0.2 t dt. Do I need to put absolute values around this? No, because 100 e to the whatever is a positive function. Remember, e has that horizontal asymptote. All right, so math 9, 4 to 6, 100 e to the negative 0.2x dx. 74, we always round to 3 places, so I'm going to say 74.067. Now we're talking about people here, so find the number of people. I would say that's about 74 new people. All right, that's it for today. I believe we have a homework assignment to go with this, possibly number 25, but I'm kind of losing track of my days here. So just check Schoology.